On November 10th, the satellite announced that ThreeI Atlast was believed to have lost a part of its body after its most recent encounter with the Sun. The celestial object ThreeI Atlast, after passing perihelion, was calculated to have lost at least 13% of its total mass, equivalent to about 4 billion tons of material. Basic physics states that such a violent outgassing event should have produced a massive tail, a spectacular stream of debris stretching millions of kilometers. However, images sent back by China's Tianwen-1 orbiter from Mars orbit revealed a puzzling silence. Instead of a bright extended tail, we saw only a dim sphere of light with no visible debris and no clear tail. Where did the 4 billion tons of material go? This is the 10th anomaly in a series of irregularities. In total, there are 10 independent behaviors that break the models we have observed in thousands of comets. When multiplying the probabilities of these 10 anomalies together, the likelihood of all occurring naturally drops below 1 in 10,000, and maybe even lower than 1 in 100,000. Astronomers are now asking, is this object representing an extreme natural phenomenon we have never seen before, or does this pattern suggest something else, something we currently have no framework to understand? The journey of ThreeI Atlast is still far from over. We will continue to follow it through its latest developments, and right after this comes the 10th declaration about an anomaly that has broken every known law of comets. ThreeI Atlast came into focus only because a distant machine dared to look where no human telescope could. While observatories on Earth stared at other targets, the Chinese Mars orbiter Tianwen-1 quietly received a new directive. Its mission was to turn away from Mars, its home of 4 years, and aim its precision cameras toward an object 30 million kilometers beyond. That object, moving faster than any known natural body in the solar system, was ThreeI Atlast. Atlast was travelling at 58 kilometers per second, roughly 129,000 miles per hour. In less than 20 minutes, it could have circled Earth once. Its solid core, only 5.6 kilometers wide, was the size of Manhattan, but darker than asphalt and colder than steel. Tracking such a small dim fragment demanded perfection. Tianwen-1 systems were designed for planetary surfaces bright, static, predictable. Now they had to follow a racing ember that moved across the sky faster than their targeting algorithms were ever meant to handle. For weeks, engineers recalibrated the orbiter. Every correction was a gamble between precision and failure. A fraction of a degree off and ThreeI Atlast would vanish into the black forever. Then the effort succeeded. CNSA released a set of raw monochrome images showing a faint sphere wrapped in a soft expanding glow, the coma of Atlast extending thousands of kilometers into space. Those frames were sharper than anything from Hubble, crisper than James Webb, more revealing than any ground telescope could ever deliver through the atmosphere. For the first time, humanity had captured a direct portrait of an interstellar visitor in motion. ThreeI Atlast was no longer a hypothesis traced by equations, it was an object with light form and presence. Yet the images carried more than triumph. They carried contradiction. The halo of ThreeI Atlast was strangely smooth, almost serene, lacking the jagged jets and vapor trails expected from a body under such heat and stress. Where physics predicted chaos, the camera found order. Where light should have flared and fractured, it shimmered evenly like breath held in space. ThreeI Atlast had turned a feat of engineering into a paradox of nature. Tianwen-1's success revealed more than a picture, it revealed a silence. And in that silence, the mystery began. When ThreeI Atlast crossed its closest point to the Sun, something measurable but invisible occurred. The object deviated from the orbit gravity predicted, moving as though a hidden force were at work. NASA's Jet Propulsion Laboratory confirmed that ThreeI Atlast was experiencing non-gravitational acceleration, a faint but persistent push produced when material leaves a body fast enough to change its motion. The data were precise. At 0, 9 astronomical units from the Sun at last's radial acceleration was 1.1 s10^6 AU day 2, pushing it outward. Its transverse component running along its orbital track measured 3.7 10^7 AU day 2. Those numbers, when entered into the equations of momentum conservation, pointed to one conclusion. ThreeI Atlast had shed nearly 13% of its total mass. That equals about 4 billion tons of material rock gas and volatile ice, expelled into space within only a few days. Physics demands that such loss blaze across the sky in the form of a brilliant tail, yet Tianwen-1, Mars Express and ground observatories saw nothing. 3. Atlast remained a dim sphere wrapped in a steady glow with no plume, no fan of dust, no turbulence. Acceleration was real, but the evidence of thrust was gone. Scientists ruled out sensor error. Each independent probe measured the same vectors. ThreeI Atlast had moved by its own momentum, but the mechanism behind that movement had erased its signature. It was a propulsion without exhaust, a reaction without residue. For astronomers, this was the first verified contradiction motion that left no trace, and in that contradiction, ThreeI Atlast whispered the beginning of its greater mystery. ThreeI Atlast entered the solar system as if it had known the layout beforehand. Its path was not random, not erratic, not the scatter expected of an interstellar castaway. Instead, it slipped through our cosmic neighbourhood, almost perfectly aligned with the ecliptic plane, the thin invisible sheet where all our planets travel around the Sun. Measurements showed a tilt of barely 5 degrees so small it fell within the precision margin of planetary formation itself. That alignment was the first alarm. For billions of years, comets formed within this plane because they were born here spun from the same disk of gas and dust that made Earth, Mars and Jupiter. But ThreeI Atlast was born elsewhere beyond the Sun's influence, ejected from another system entirely. Its orbit should have been chaotic, slanted or vertical. Statistically, an interstellar object should approach from any direction in three-dimensional space, unconstrained by our local geometry. Yet ThreeI Atlast came in nearly flat, tracing the same path as our own planets, but moving in the opposite direction. Retrograde motion within a coplanar orbit is not a mere curiosity, it is a mathematical contradiction. To travel opposite the planetary flow while staying confined to the same disk requires immense precision. It's like a leaf sliding upstream along the surface of a river without ever drifting above or below the current. The odds of that happening by accident are tiny. If interstellar trajectories are distributed evenly across the sky, the probability of one entering within 5 degrees of the ecliptic is roughly 0.2%, 1 in 500. Astronomers double-check the data. Early calculations might have been distorted by short observation windows, they thought, but independent analyses from JPL ESA and CNSA confirmed the same orbit, the same alignment, the same geometry, the same retrograde flow. ThreeI Atlast was truly coplanar with the solar system, moving against its grain like a shadow in reverse. No natural mechanism explains this easily. Ejection from a foreign star system is typically chaotic, dictated by gravitational slingshots that fling debris in all directions. For ThreeI Atlast to end up so perfectly aligned implies either an improbable coincidence or a hidden pattern in galactic dynamics. Some researchers suggested it might belong to a larger stream of interstellar debris following the Milky Way's gravitational mid-plane. If that were true, Atlast's orbit could reflect the natural curvature of galactic matter, but no evidence of such a stream has ever been observed. Others wondered if the alignment itself carried purpose, a path optimized to intersect with the planetary plane deliberately, perhaps to maximize observational opportunity or gravitational assists. Emotionally, the discovery unsettled the scientific community. The ecliptic is more than a coordinate plane, it is our cosmic foundation, the stage upon which all known motion unfolds. For ThreeI Atlast to enter through that same plane, aligned level, inverted, was like seeing a foreign signature written in our own handwriting. The anomaly stood on its own geometry, too precise probability, too small and motion too elegant to dismiss. It was the first undeniable deviation the moment the ordinary language of celestial mechanics began to fail. And from that perfect silent alignment, the mystery of ThreeI Atlast opened its first chapter of defiance against randomness. ThreeI Atlast violated one of the simplest and most reliable laws in cometary physics. Between July and August 2025, telescopes around the world recorded something no natural comet had ever done: a jet of material erupting toward the Sun instead of away from it. Every rule of thermodynamics, radiation pressure and solar wind dynamics says that is impossible. Yet the images were undeniable. Comets shed material as sunlight heats their surface, gas expands, dust escapes, and the released particles are pushed outward by the pressure of sunlight, forming a long tail that always points away from the Sun. This rule is so absolute that astronomers use tail direction to identify a comet's position even without tracking its nucleus. But ThreeI Atlast defied that compass. Its ejected stream didn't retreat from the Sun, it advanced toward it. At first, scientists suspected an optical illusion. Certain viewing angles can make a normal tail appear, inverted the so-called anti-tail effect when Earth passes through the comet's orbital plane. but multiple independent observatories in Chile, Japan, and Italy confirmed the same orientation at the same time. Geometry could not explain it. ThreeI Atlast was truly emitting material into the face of the Sun directly against solar radiation pressure. That directionality is physically absurd. For a natural jet to point sunward, it would require a rotational configuration so extreme that centrifugal forces would tear the nucleus apart. Even then, the expelled gas should have been deflected instantly by solar wind bending the stream backward within seconds. Instead, the jet from ThreeI Atlast held its vector steady for nearly 48 hours, a sustained defiance of the forces acting upon it. Some proposed that perhaps a magnetic field had redirected the flow, but the interplanetary field near 1AU is far too weak for such precision. Others hypothesized an asymmetric surface cavity focusing gas through a narrow vent, but that would still not explain the directional persistence of the emission. The jet acted less like vapor from a vent and more like thrust from a controlled nozzle. Emotionally, the data disturbed even the most grounded scientists. The image of ThreeI Atlast, a distant traveller pushing against the sun itself, resonated with something almost mythic. It was as if the object were testing the star's dominance, performing an act no natural body should attempt. That sense of rebellion was not poetry. It was physics refusing obedience. The anomaly was officially logged as jet emission oriented towards solar vector. Behind that sterile phrase lay an unspoken realization a force was acting with intent-like precision, contradicting the passive nature of outgassing dynamics. ThreeI Atlast was not simply reacting to sunlight, it was maneuvering through it. In the long record of cometary science, tales have always fled from the sun like shadows from fire. ThreeI Atlast, for reasons still unknown, turned to face the light and moved against it. ThreeI Atlast was immense, fast, and statistically impossible. Its nucleus stretched roughly 5.6 kilometers across an icy metallic city, adrift between the stars. That alone made it extraordinary, but its speed transformed it into an astrophysical paradox. At 58 kilometers per second relative to the Sun, or about 129,000 miles per hour, Atlast was travelling faster than any object of its class ever observed. Size and speed are not supposed to coexist in nature. The larger the body, the harder it is to accelerate. Astrophysics teaches this rule with the precision of mathematics. Small fragments can be flung into interstellar space by gravitational ejection, but a massive kilometre-scale object requires a staggering amount of energy to reach escape velocity. ThreeI Atlast broke that balance. It wasn't just large, it was also moving too fast to belong anywhere. For comparison, the first interstellar visitor, Oumuamua, was a lightweight shard, maybe 100 meters long, tumbling quietly through space. The second 2I Borisov was larger, a typical comet with a core only a few hundred meters wide, but ThreeI Atlast dwarfed them both, over 1,000,000 times more massive than Oumuamua and 1,000 times heavier than Borisov. Statistically, such an object should be among the rarest in the galaxy, and yet the third interstellar body ever found was also the largest and fastest. Models of galactic dynamics do not allow this combination easily. High-velocity ejecta tend to be small fragments scattered during planetary collisions or stellar flybys. Massive bodies, on the other hand, remain gravitationally bound to their home systems. To accelerate something as massive as ThreeI Atlast to such speed would require either a catastrophic event, a near pass by a neutron star or black hole, or a deliberate act of propulsion. Neither scenario fits comfortably within known probability. Researchers tried to reconcile the data. Perhaps the measured velocity included solar gravitational acceleration. No Atlast's speed before entering the heliosphere already exceeded interstellar escape velocity. Could it be part of a hyperbolic stream of similar objects, remnants of galactic tides? Possibly, but no other objects shared its trajectory. It was singular alone, defying distribution models by orders of magnitude. Emotionally, astronomers described ThreeI Atlast as a statistical rebellion. Every rule of probability said it shouldn't exist, yet there it was crossing the solar system like a projectile forged from the improbable. Its presence forced an uncomfortable question. Was Atlast a cosmic accident of staggering unlikelihood, or was it a traveller launched with intention? The anomaly's summary was clinical but haunting. Detected object exhibits extreme mass-velocity coupling inconsistent with stochastic ejection profiles. Translated into human language, it was too big, too fast, too perfect a bullet. A natural object can break a rule, but rarely two at once. 3. Atlast broke both and continued onward as if to remind us that the universe, even when governed by laws, still allows for defiance. 3I Atlast did not simply enter the solar system. It arrived, and it did so with a precision that mocked coincidence. Every stage of its trajectory appeared to synchronize with our instruments, as if following an invisible choreography. From the moment it crossed Mars's orbit to its passage near Venus and Jupiter, Atlas seemed to know when and where our eyes would be. In September 2025, Atlas swept past Mars, grazing within tens of millions of kilometers, close enough for high-resolution imaging. At that very moment, the European Space Agency's orbiters, Mars Express and Trace Gas Orbiter, happened to be positioned perfectly for observation. Weeks later, Atlast's path curved near Venus again, during an operational window when probes around the planet were active. Finally, it passed the outer reaches of Jupiter's domain, close enough for long-range detection, yet far enough to avoid gravitational disruption. Each encounter was geometrically and temporally ideal. The pattern might have gone unnoticed if not for what followed. During perihelion, the moment when Atlast approached within 0.9 AU of the Sun, closer than Earth, and nearly the orbit of Venus, it should have shone brighter than ever. But at that very instant, the Sun aligned directly between Atlast and Earth. From our planet, the object became completely invisible. For weeks, every ground-based telescope on Earth was blinded by daylight in the same direction Atlast passed through. It was the most unobservable moment possible. This perfect concealment raised more than eyebrows. The odds that an interstellar visitor would by pure chance pass directly behind the Sun from Earth's vantage point precisely during its brightest phase were calculated at 0.005% or 1 in 20,000. It was as though the cosmos had dimmed the lights on purpose. Researchers tried to dismiss the implication. Perhaps it was luck timing written in randomness. But the alignment benefited one perspective only orbital spacecraft, not Earth. From Mars's orbit, from Venus's neighbourhood, and from Jupiter's distant gaze, the object remained visible long enough to be recorded. From Earth, it vanished. To any system designer, such a trajectory would appear optimized for reconnaissance, a flight path skimming major observational posts while avoiding the most watched point in the sky. Emotionally, the realization left a strange unease among astronomers. 3I Atlast seemed to be aware of our geometry. Not in the literal sense, perhaps, but its path behaved as though it respected the architecture of our observation network. In a century of celestial tracking, no interstellar object had ever arrived with such theatrical precision. The scientific report summarized the event in neutral terms: solar conjunction, rendered object unobservable from Earth at perihelion. Behind those words lay something deeper, the feeling that 3I Atlast had executed a maneuver no random body could time so perfectly. It was the fourth anomaly, the one that made chance begin to sound like intention, and as Atlast continued its precise exit from the inner solar system, the question lingered in every observatory log: who or what had planned such an immaculate disappearance? 3. ThreeI Atlast was not only a mystery of motion, it was a riddle of matter itself. When its coma was first analysed through spectral decomposition in mid-2025, astronomers expected the familiar fingerprint of volatile ices and silicate dust. Instead, they found a metallic echo-nickel, and more of it than iron. In all of cometary science, such a ratio had never been observed. Ordinary comets within the solar system follow a consistent pattern. Iron dominates, nickel follows, and trace volatiles round out the spectrum. The proportions are predictable, written by the chemistry of solar birth. 3I Atlast broke that symmetry completely. Its spectral lines blazed with nickel intensity, stronger, sharper, and chemically inverted. The ratio of nickel to iron was not merely skewed, it was reversed. Where nature favoured iron, Atlas favoured nickel. Even more astonishing was the abundance of nickel cyanide compounds, far beyond anything recorded in known comets. Their signal was stronger by orders of magnitude 10, perhaps 100, perhaps 1,000 times the standard value. It was a chemical composition so foreign that the data teams at both ESA and JAXA initially flagged it as instrument contamination. Repeated calibrations ruled that out. The readings were real. The discovery forced astrophysicists to reconsider what kind of star system could produce such a composition. Nickel-dominant chemistry might suggest a world formed close to a hotter, older star one whose nebular environment forged denser metallic cores. But even that scenario failed to explain the sheer purity of the signature. Natural formation models do not produce such an extreme nickel preference without leaving secondary traces of iron or magnesium. ThreeI Atlast's spectrum was almost engineered: selective, deliberate, efficient. In laboratories, that same ratio is found in industrial nickel alloys, materials used on Earth for spacecraft and heat shields, chosen for their resistance to stress corrosion and thermal decay. The resemblance was disquieting. The data did not prove artificial origin, but the comparison was hard to ignore. If one were to design a vessel or probe to survive the violence of interstellar travel for millions of years, a nickel-based structure would be among the most logical choices. Emotionally, the revelation marked a turning point. Up to this point, the anomalies of ThreeI Atlast could still be argued as mechanical coincidences of orbit or light. But the substance of the object, cut deeper. This was the first time nature's handwriting looked almost human. The official report phrased it cautiously: spectral data reveal anomalous nickel enrichment inconsistent with known cometary formation environments. Behind those words lay a quiet astonishment shared across observatories. ThreeI Atlast was not made of the same dust as the rest of the solar system. It was harder, denser, older, as if forged in a furnace beyond ours or crafted by hands unseen. ThreeI Atlast shattered yet another cornerstone of cometary physics. It was almost dry. Where a comet should be a dirty snowball, this visitor was closer to a metallic stone wrapped in a whisper of frost. Spectral analysis revealed that only 4% of its total mass consisted of water ice. For comparison, typical comets in our solar system contain 70 to 80% water. This was not a comet in the conventional sense. It was something else entirely. The first reaction from astronomers was disbelief. Water is the heartbeat of cometary activity. It vaporizes under solar heat, drives jets, and forms the brilliant tails we see from Earth. If Atlas lacked water, then what was fueling the massive outgassing and non-gravitational acceleration detected during its solar pass? The physics did not add up. Theories began to fracture. Some scientists suggested that ThreeI Atlast may have originated in an unusually hot star system, one where volatile materials evaporated early, leaving only metallic cores and silicate crusts. Others proposed that it had once been an asteroid-like body that later collected thin layers of volatile dust as it drifted through interstellar clouds. Yet even those explanations strained under the numbers. Atlas did not merely lack water, it behaved as though it had been designed to survive without it. Natural comets erode. They shed their ices, crack and fade with each solar encounter. But ThreeI Atlast endured its structure solid, its reflective coma faint but persistent. A body with so little water should have disintegrated under the same heat that stripped billions of tons from its surface. Instead, it remained cohesive. It resisted fragmentation. It acted in every measurable way like something built for endurance. The more data scientists collected, the stranger the object appeared. Without significant water, Atlast's jets must have been powered by other compounds, perhaps nickel vapors, silicate gases, or something we do not yet understand. Whatever the process, it was efficient, stable, and sustained for weeks around perihelion. This was not chaotic evaporation. It was a regulated release. Emotionally, the realization unsettled even seasoned astronomers. ThreeI Atlast did not fit the story of a wandering ice relic from another star. It fit the image of a traveler hardened by time, shaped for survival, stripped of all fragility. The thought was both awe-inspiring and deeply uncomfortable that we might be witnessing an interstellar body engineered not for beauty but for persistence. Official reports worded it carefully. Observed a volatile fraction is anomalously low. Primary composition inconsistent with standard cometary ice models. But between those lines, the implication grew louder. A comet made of almost no water is a contradiction. A comet that still accelerates, still outgasses, and still holds together despite that dryness, that is a message written in the language of endurance. ThreeI Atlast may not have carried oceans, but it carried something rarer, the ability to defy the very definition of what a comet is. And in that defiance, it left us wondering, was this the universe's most resilient wanderer, or the oldest artifact adrift in the dark? When light met the surface of ThreeI Atlast, it behaved as though it were encountering something alien. Ordinary comets scatter sunlight in a predictable way, a pattern well documented across decades of observation. The reflection creates partial polarization, where the oscillation of light waves aligns according to the texture, size, and composition of the dust. Every comet ever studied from Halley to Borisov followed this same optical grammar. ThreeI Atlas broke it completely. Measurements taken during its solar approach showed an extreme negative polarization, a signature so rare that no known natural model could reproduce it. Instead of reflecting light in the expected alignment, Atlas twisted it, bending polarization backward as if the surface were absorbing one component of light while inverting the other. The data stunned astronomers. It wasn't noise or instrument error. Multiple observatories confirmed the same effect from Italy to Japan to the Mars orbiters that caught its faint halo. In layman's terms, ThreeI Atlast was bending light the wrong way. Its reflected rays implied a surface far smoother or denser than any dusty comet nucleus. Some hypothesized metallic microstructures perhaps fused nickel grains or ultra-fine crystalline films that could create this inversion. Others proposed a coating of plasma-charged dust, aligned by magnetic fields producing an artificial optical filter effect. But all these ideas remained conjecture. Nothing in nature, as far as our telescopic archives reveal, had ever produced such polarization. Under conventional physics, negative polarization occurs only at specific scattering angles in rare minerals or engineered materials. To find it in a body millions of kilometers away, and at magnitudes beyond any lab replication, was a statement of impossibility. ThreeI Atlast didn't just reflect light, it manipulated it. The data curves looked almost like those seen in laboratory laser experiments, not cometary surveys. Emotionally, the discovery hit the astronomical community with a quiet awe. It wasn't the loud drama of impact or explosion, it was the subtle defiance of optical truth. Every photon returning from Atlast whispered that its surface was something we did not understand, smooth yet, not polished, reflective, yet not bright. If the universe has languages we cannot read, this was one of them. The official summary tried to remain neutral. Observed polarization angle and intensity deviate significantly from all modelled scattering regimes. Behind the restraint of those words, scientists felt the unease of recognition that this interstellar traveller carried with it not just physical anomalies, but material laws rewritten. ThreeI Atlast was already known for its impossible orbit, its missing tail, its strange acceleration. But in the polarized light that spun across its skin, the cosmos revealed a deeper truth. The object wasn't merely strange, it was instructive. It was showing us how much of physics we still didn't know, and perhaps how much of it we had never yet been meant to see. Among all the strange alignments surrounding ThreeI Atlast 1 stood out for its eerie echo across nearly half a century. The trajectory of this interstellar object pointed back toward the same region of sky that once produced the WOW signal, the most famous and unresolved radio mystery in SETI history. The coincidence was not exact, but the proximity a mere 9 degrees apart was close enough to draw every scientist's attention. The WOW signal, recorded on August 15, 1977, came from the constellation Sagittarius near the Chi-Sagittari region. It lasted for 72 seconds, narrowband, powerful and never repeated. Astronomers called it WOW because that single handwritten note penned by Jerry Eman beside the signal's printout became an immortal symbol of curiosity. For nearly 50 years, no one has ever found its source. Then came ThreeI Atlast, emerging from a matching celestial corridor, moving along a path intersecting that same sector of interstellar space. No other known interstellar body, neither Oumuamua nor Borisov, shared that direction. Statistically, there are tens of thousands of possible inbound angles for an object from beyond the solar system. To enter within a 9-degree radius of a location already famous for an unexplained radio burst borders on impossible coincidence. The probability was calculated to be less than 1%. Scientists were careful not to sensationalize it. Correlation is not causation. There is no evidence linking the two events. But within the community of radio astronomers and interstellar researchers, the alignment became a quiet obsession. If the WOW signal had truly been an artificial transmission, a narrow-band call sent across space, then ThreeI Atlast appeared to come from its neighbourhood. And if it were merely natural noise, then the coincidence was still extraordinary enough to warrant re-examination. Several teams rescanned the region during Atlast's approach, hoping to detect any repeat signal. None appeared. But the very geometry of the event, an interstellar visitor travelling from the direction of the one unresolved beacon in our radio history, kept the question alive. Had the signal and the traveller shared an origin, or had we by sheer coincidence been looking twice into the same vast, silent corridor of the galaxy? Emotionally, the realization unsettled many scientists. It was not fear, but a sense of profound symmetry, that perhaps the universe was repeating a whisper we once heard but never understood. ThreeI Atlast had already broken the laws of motion composition and light. Now it seemed to trace its lineage through the coordinates of mystery itself. The report from the SETI Research Network concluded with unusual restraint. The trajectory of ThreeI Atlast intersects within 9 degrees of the historical WOW signal origin. Statistical likelihood of coincidence, lost at 6%. No speculation followed, only a footnote, simple but haunting. Further investigation recommended upon detection of future interstellar objects entering from similar coordinates. ThreeI Atlast came and went without broadcasting a sound. Yet in its silence it reignited the echo of a message sent long before it arrived, a message that still waits unanswered in the static between stars. The night of October 29, 2025 began like any other for astronomers watching the inner solar system. But within hours, data streams from Chile, Hawaii and orbiting observatories all reported the same unexplainable spike. ThreeI Atlast had brightened fivefold, a surge so abrupt, so clean, that it seemed less like a flare of nature and more like a signal switch. The intensity rose not gradually, but in a single flawless pulse. Ordinary comets brighten when they release gas and dust near the sun. The ice sublimates, sunlight scatters through vapour, and a diffuse glow grows around the nucleus. It's messy, chaotic and dusty, always yellow-white, never blue. But ThreeI Atlast refused to obey that rule. When its luminosity spiked, its light spectrum shifted toward the blue cold metallic sharply defined. The readings resembled ionized plasma emissions, not the warm scattering typical of cometary dust. No debris cloud was detected, no water vapor signature. Tianwen-1 and the ESA's solar orbiter both confirmed that the object's coma remained unnaturally smooth uniform, in shape perfectly symmetrical. The brightening appeared without loss of mass, a contradiction that broke the heart of comet physics. Energy had increased, but nothing burned away. Scientists rushed to find an explanation. Could it be an instrumental artifact sensor, saturation, optical reflection, cosmic ray interference? All three were ruled out within hours. Independent observations matched perfectly across wavelengths and latitudes. ThreeI Atlast had truly brightened not by reflection but by emission. Some hypothesized a plasma sheath event where solar particles interacted with a charged metallic surface, briefly exciting it into fluorescence. If so, that would mean the body was conducting electricity, an interstellar traveller acting as a colossal capacitor in the solar wind. Others speculated about internal activity, piezoelectric reactions within a compressed crystalline lattice, releasing sudden bursts of energy. Both ideas bordered on the impossible, yet both fit the data better than dust and ice ever could. Emotionally, the moment left a strange stillness in observatories worldwide. ThreeI Atlast had already challenged gravity and composition. Now it seemed to challenge the meaning of luminosity itself. The blue glow it released was not chaotic, not random. It pulsed with measured steadiness, lasting 70 days before fading back to normal. No comet in recorded history had ever maintained such constant brightness for so long without disintegration. The official summary reduced the event to 4 sterile words: unexpected sustained photometric enhancement. But those who saw the live data described it differently. They said the light of ThreeI Atlast didn't shine, it spoke. It was the colour of deep space lightning, the hue of something alive within silence. And though the surge ended as suddenly as it began, its echo remained a single spectral signature that marked the moment the cosmos blinked back at us. In every rulebook of celestial mechanics, there is one certainty: when a comet loses mass, it must show it. The tail, that blazing ethereal stream, is the visible proof of destruction. Yet when ThreeI Atlast passed perihelion and lost an estimated 13% of its total mass, amounting to roughly 4 billion tons of material, the sky remained disturbingly blank. There was no plume, no drift of dust, no vaporized halo stretching into the void. Just a dim spherical glow, the silence where chaos should have been. Telescopes from Spain, Italy and Mars orbit all confirmed the same absence. The direction opposite the Sun, where the tail should have been dragged by solar pressure, showed nothing. Even deep field analysis at long exposure revealed no debris, no trailing filament of gas. The universe had stolen the comet's scream. ThreeI Atlast was supposed to bleed light and matter, but it chose to remain intact, sealed within its own quiet boundary. This anomaly cut to the core of astrophysical logic. To produce the measured non-gravitational acceleration, the subtle push detected by NASA's JPL data Atlast had to expel enormous momentum. Momentum demands mass loss. Yet the expelled mass was missing from every instrument and image. Where did those 4 billion tons go? Was it dispersed invisibly as superheated plasma, or was it redirected through a mechanism we've never recorded? Some propose that the ejected material might have been ultrafine gas, composed of molecules so small and hot that they emitted outside the optical band invisible to visible light telescopes. Others suggested the possibility of phase-shifted reflection, where charged particles formed an electromagnetic cocoon that trapped the outflow, redirecting it inward instead of outward. A few dared to mention a propulsive event, not venting, but deliberate redirection of expelled material mimicking thrust. But such speculation teetered between astrophysics and engineering. The emotional weight of this anomaly struck differently than others. It wasn't flamboyant like the blue flare or mysterious like the wow alignment. It was an absence, a vacuum in expectation. Astronomers stared at high-resolution composites, where a luminous streak should have carved across the darkness, and saw only nothingness. The emptiness itself became data, a measurable lack that defied both optics and physics. The official summaries were restrained as ever, no visible dust tail corresponding to the recorded acceleration. Possible composition anomaly. Behind those calm words, every scientist knew this was something deeper. A missing tail meant missing proof. The very evidence that should confirm what was happening had vanished with the act itself. It was as if ThreeI Atlast had decided to erase its own trail while performing the event that proved it was alive. In the aftermath, some compared it to a ship crossing an ocean without leaving a wake, not because the water was still, but because the ship commanded it to be still. ThreeI Atlast broke not only the visible laws of motion, but the visual poetry of comets themselves. A comet without a tail is like a voice without sound, and yet somehow the silence it left behind was louder than any explosion in the solar system. When the data from ThreeI Atlast was first consolidated, 10 distinct anomalies, each seemingly impossible on its own, the initial reaction across observatories was disbelief. Not skepticism in the hostile sense, but the quiet, professional refusal to jump ahead of evidence. Astronomy, after all, is built on patience and probabilities. Yet as those probabilities were multiplied, the comfort of chance began to collapse under its own numbers. Each anomaly carried its own statistical weight, a quirk of alignment within 5 degrees of the ecliptic 1 in 500, a sunward jet defying radiation pressure 1 in 1,000, a trajectory synchronized with planetary observation windows 1 in 20,000. When combined and assuming independence, the probability that all 10 anomalies could coexist by random chance dropped below 1 in 100,000, perhaps even 1 in a million, depending on the correlation model. That number was not a claim of design. It was a whisper that nature, while vast, had just presented something bordering on the statistically absurd. Astrophysicists at the Harvard-Smithsonian Center ran Monte Carlo simulations using data from over 2,000 known cometary orbits. None replicated the Atlas pattern. European teams at ESA modelled sublimation-driven jets. Under extreme thermal and rotational conditions, still no configuration could explain the sunward ejection or the absent tail. Meanwhile, at Caltech's Jet Propulsion Laboratory, analysts checked the non-gravitational acceleration dataset for bias. The vectors held. The thrust was real, and yet there was no source for it. For most of the scientific community, the rational stance was simple. Anomalies require data, not drama. ThreeI Atlast would be treated as an outlier until proven otherwise. But a few researchers began to notice something that transcended mere statistics, the pattern of coherence among the anomalies. Each one reinforced the others. The high nickel content supported the metallic surface theory. The missing tail reinforced the controlled mass loss hypothesis. The sunward jet aligned with the notion of vector-regulated thrust. Individually, they were improbable. Together, they hinted at intentional coordination. This is where Avi Loeb entered the conversation not as a provocateur, but as a methodologist. Loeb's argument was never, ThreeI Atlast is artificial. It was ThreeI Atlast cannot be dismissed. His approach mirrored the same logic he once applied to Oumuamua when a dataset contains multiple low-probability events that converge on a single physical system. The responsible act is not to reject the data, but to widen the hypothesis field. That principle, epistemic humility through expansion, quickly divided the field. Institutions like NASA, ESA, and the Chinese CNSA maintained conservative stances. Their official reports favoured compositional explanations, metallic aggregates, exotic chemistry, or interstellar erosion over millions of years. But informal workshops told a different story. In late November 2025, a closed symposium at the Max Planck Institute, brought together orbital analysts, plasma physicists, and SETI researchers. The conclusion, recorded but never formally published, read: "The dataset for ThreeI Atlast presents a non-trivial clustering of statistically independent irregularities. Further study should proceed without presumption of naturality or artificiality." That single phrase, "without presumption," became a quiet rallying cry for the younger generation of astronomers. For decades, astrophysics had been built on the assumption that all cosmic behaviour could be traced to natural processes even if not yet understood. ThreeI Atlast disrupted that comfort. It was not the suggestion of alien design that shook people, it was the realisation that our models might be too narrow to hold reality's complexity. Emotionally, this period marked a turning point. For many scientists, it recalled the early days of quantum mechanics, when certainty gave way to probability, and probability to paradox. Atlas, like those first particles that refused to behave, stood at the threshold between the measurable and the incomprehensible. Its silence mocked both arrogance and awe. Each new analysis, each failed simulation became a meditation on the limits of human inference. By December 2025, the consensus was paradoxical. Everyone agreed on the facts and no one agreed on their meaning. The statistical models were airtight, the observations cross-verified, the anomalies undeniable, and so the debate moved beyond data into philosophy, method, and belief. Was ThreeI Atlast a random masterpiece of physics, a convergence of impossibly rare conditions born from chaos? Or was it the first whisper of structure from beyond our frame of reference, a sign that intelligence, natural or otherwise, had once brushed against our sun? Science could not yet answer. But one truth had already emerged. ThreeI Atlast had forced the world of astronomy to look not only outward but inward into the fragile boundary between knowing and wondering, where discovery truly begins. ThreeI Atlast, by every traditional measure, should not exist, or at least not in the form we saw it. And yet the simplest hypothesis, the one favoured by most astrophysicists, is also the most conservative. ThreeI Atlast is natural, an anomaly, yes, a statistical outlier born from the unthinkable diversity of the cosmos. To understand this stance, one must first confront the scale of creation. Our galaxy alone holds over 100 billion stars each, encircled by clouds of gas, ice, and debris. Every one of those systems is a random experiment in chemistry, gravity, and temperature. Across such immensity, the improbable becomes inevitable. Somewhere in the silent churn of those billions of orbits, one object could emerge that defies every rule drawn from our narrow sample of 3 known interstellar visitors. To call Atlast impossible is to forget the mathematics of infinity. In this hypothesis, ThreeI Atlast is the natural extremity of possibility. Its high nickel content, its near-total absence of water, its plasma-like behaviour, all are the result of formation within a radically different environment. Perhaps it was born close to a hot massive star where lighter elements boiled away. Perhaps it was forged within a system rich in heavy metals sculpted by forces that left its crust dense and magnetic. If so, Atlast is not an alien artifact, but a geological messenger, a sample from a world older and harsher than ours. The advocates of this model point to precedent. Science has seen this pattern before. When the first pulsars were discovered, their perfect periodic signals were briefly labelled LGM1, little green men. Only later did we learn they were spinning neutron stars, not transmitters. When gamma-ray bursts were first detected, they too seemed artificial, until we traced them to dying galaxies. Nature is often stranger and more inventive than intention. To assume ThreeI Atlast is artificial may simply repeat that same mistake, confusing unfamiliarity for design. Statistically, the reasoning is straightforward. If the galaxy hosts trillions of comets and planetesimals, even an event with a probability of 1 in a million is not a miracle. It's an eventuality. In that sense, Atlast is a living embodiment of the law of large numbers, proof that given enough cosmic rolls of the dice, something impossible will always appear. As one scientist at the European Southern Observatory put it, the universe is big enough to surprise us without cheating, and yet even within this hypothesis, unease lingers. Explaining 10 independent anomalies as separate accidents requires an uncomfortable stacking of coincidences. A nearly planar orbit could happen by chance. So could a metallic composition. So could a missing tail. But when all appear in the same object, probability turns into poetry, and poetry makes scientists nervous. Supporters of the statistical outlier model counter this discomfort with humility. They argue that our catalogue of interstellar visitors is too small to define normal. 3. Atlast is only the third such object we've ever seen. To build theories from 3 data points, they say, is like predicting the ocean after watching 2 waves. Perhaps Atlast is not the outlier. Perhaps everything else is. Emotionally, this perspective offers comfort. It allows humanity to stay within the realm of the known to keep wonder tethered to reason. Atlast becomes not an intruder, but a teacher. Its contradictions are not signs of intelligence, but lessons in humility. Each deviation expands our models, forcing us to accept that our solar system's physics is not the universe's physics. By the close of 2025, the statistical outlier remained the official position in most journals and conferences, not because it explained everything, but because it required no miracles, only patience, data, and time. If 3I Atlast is truly natural, then it is a gift from the cosmos, a sample of the rare, the extreme, the unexpected. And if future visitors prove it was unique, that too will be a revelation. In science, rarity is not weakness. It is evidence that the universe is still larger than our imagination. 3. Atlast came and vanished without a word. No transmission, no message, only the trail of questions it left behind. It reminded us that the universe does not reveal itself in answers, but in riddles that demand courage to face the unknown. Perhaps we will never know what Atlast truly was, a relic of nature or an echo of design, yet its passing changed how we look at the sky. Because from now on, every flicker in the dark carries a whisper of possibility, and that more than proof is what keeps humanity looking up.